All right. Well, hi everybody. Thanks for the introduction. So my name's PC Simon. I work at Idaho National Lab, and I'll be talking about a collaboration that started a year and a half ago now. That is modeling magnetic confinement fusion system with MOOS-based capabilities. I say a year and a half for the overall project, but MOOS started, 15 years ago at Idaho National Lab, and is building on top of that. I wanted to highlight some of the collaborators here from NC State, University of Illinois, the UK AEA, but also VCU that you can see here, and it's really a group effort. So the overview is that we're basing everything on MOOS, and I'll share some links in the chat right after. But we're basing things on MOOS, which is a flexible platform for multiphysics simulation. It's open source. It follows high software quality assurance. I'll talk about this in a minute. And it's been used quite extensively in the fission space to support high-fidelity modeling of the design, safety analysis, optimization, science and engineering studies of fission systems, and we want to use it for fusion. The main motivation here for those modeling and simulation capabilities came from this PhysAct report from 2020, where to accelerate fusion deployment, we need multi-scale multiphysics modeling and simulation capabilities that can understand the interactions between plasma, material behavior, and engineering processes. And I'll go even further and say that it's important to have capabilities that can help scientists and engineers work together. And I'll try to show how we can enable that. And so MOOS is well suited for this challenge. And what we've been doing is building on top of that framework for application in fusion. So this is an overview of the capabilities that we are putting together here. And it's kind of understanding the interactions between the multiphysics in the fusion blanket and plasma-facing component for magnetic confinement. So MOOS is the overall platform that helps us solve the PDEs on a finite element using a finite element method. And it has specific modules. And some of the modules are the heat conduction modules. Can you see my arrow? I hope you can.
Yes, we can.
Okay, awesome. So the heat conduction module, the thermohydraulic module, and thermomechanics. So those things have already been developed, verified, validated, etc. And so we're coupling those together. One that we've been developing since 2019 roughly is TMAP8. I'll talk a little bit about what TMAP8 does, but in essence, it does tritium transport. And so what it needs from the other capabilities is the temperature. We could also imagine the stress state coming in, etc. We also leverage Cardinal, which is a MOOS-based application that basically wraps around OpenMC and NECRS. And so it enables other MOOS application to be tightly coupled with things like OpenMC, which is what we're using here for neutronics. And that provides, for example, a generation rate for the tritium transport or the heating rate for the heat conduction, etc. So really a key piece of the coupled physics. And then the protocol in cell is part of the physics that we are developing in-house as well within that framework to do some of the plasma kinetics and provide some of the source term for the neutron, but also heating rate. And also actually some implantation profile for TMAP8. So that's the overview. Now for TMAP8 in particular, so I'll share some link in the chat or you can scan this code. But I now had developed TMAP4 and TMAP7 for tritium transport. And it has been widely used, but it had significant limitation. It was developed in Fortran. It was export controlled. It couldn't be used on high-performing computing systems. It was limited in number of traps it could account for, etc., etc. The advantage here is that we're building TMAP8 on top of MOOS, so it inherits all of those capabilities that it already has, like ability to do high fidelity, ability to do multi-scale, 3D simulation, multi-physics simulation for tritium transport. And also it's open source. We follow the same guidance as MOOS or other MOOS-based tools in terms of software quality assurance. So we are nuclear quality assurance level 1 compliant, and we also good user support and massively parallel capabilities. And in terms of development, I'll talk about some of those capabilities. But one of the main focus that we've had in the last few years was developing the verification and validation suite in TMAP8. So we talked a little bit during the panel discussion this morning. There was a lot of talks about how do we ensure that open source tools can be trusted and used by the industry. And we think this is a key piece, is that every capability that you have should be verified and validated so that people can trust it. And that verification and validation suite in that case is all open source. It's available on the TMAP8 website, and it's all reproducible. So we provide the input file, we provide the documentation, we provide the experimental data we compare against, and we provide a script to recreate the plots that you can see in the documentation. What we hope is that by being transparent like this and being open, that increases code quality, which is especially key for software quality assurance, especially in a topic such as tritium transport. Some other tools that we have available in TMAP8 is the stochastic tools. So Moose has a stochastic tools module that we can directly couple in TMAP8 quite seamlessly. So that can help for calibration, for example, of model calibration. It also helps with quantifying sensitivity, quantifying uncertainty, and they have a lot of capabilities here that can be used to quantify the source of errors from experimental error, model parameters, sensitivity and inadequacy of the model expression, which is really key, I think, to prioritize and strategize the next steps when you use such a tool. So if you know where the error comes from, it's easier for you to strategize what the next steps are going to be to improve your tools or experiment. Some other capabilities that we have is we have an example for the fuel cycle. So that's kind of highlighting TMAP8's capability to model the system level. But we can also do, as we said earlier, some multi-scale simulation where we here model tritium transport in at the pole scale. And then here we look at simulations of tritium transport at the component scale. So this is a divertor monoblock, and this is the modeling of fuel blanket slice. This had almost 1,000 cooling channel, different materials for the breather, the multiplier, and the first wall. And this was a simulation that was 36 million degrees of freedom, so highlighting also some of the high-performing computing capabilities. So the way that we couple all of this with neutronics is through Cardinal. So I put the link here, and I'll put the link in the chat later on. But it wraps around OpenMC in that case, and enables us to couple the OpenMC calculation with the rest of the Moose calculation, in particular the tritium transport. So you have some documentation here, and it's been used in a lot of different applications, as you can see here. Very well established tool, and open source as well. I'll go over this very quickly, but this is highlighting some of the results that we've obtained, coupling OpenMC with Moose and trying to streamline that workflow. We saw that one of the main barriers to engineering studies was creating the mesh and then making sure that we use the mesh for OpenMC or neutronics calculation, and then can transfer the information easily between OpenMC and the other physics within Moose. And so what Mahmoud and April here at UIUC have done is that they demonstrated a CAT-based workflow using those tools. And this is highlighting some of those things where we can see the OpenMC mesh and then the Moose-based mesh, and we can see how we were able to couple the neutronics in a very simplified geometry. You can see more information in the paper here. But in a very simplified geometry, seeing the tritium generation rate and then the temperature of extremely simplified donut-like design. As I said earlier, we're also developing particle and cell capabilities for plasma. So we leveraging some of the ray tracing module capabilities already available within Moose. And here again, all of the capabilities that we are developing are being verified quite thoroughly. And I think we have some this little video. Okay, started. So this is, for example, an example of verification of two-stream instability simulation where we make sure that the linear stage of the simulation is properly captured and that we verify that behavior. Some of the next steps are going to be coupling those with the electromagnetic module in MOOS to be able to do some high-fidelity simulation of the plasma. Again, you kind of see the ethos of this type of development, developing the capability, verifying the capability, and then when there's a gap is coupling it with other models or other capabilities already available within MOOS to accelerate that development and the multiphysics simulations. This is an example I wanted to highlight. So in this example, we have we're looking at the divertor monoblock behavior. So the divertor monoblock is a piece that's in the divertor in the tokamak design, and we published a paper earlier using only TMAP8 to look at heat distribution and tritium distribution within that monoblock, where we have tungsten, then a layer of copper, and then a layer of copper, chromium, zirconium. And what we're looking at here is the divertor monoblock with the heat source from the top and tritium source from the top, and we follow the pulse operation, right? So the temperature increases, stays constant for a little bit, then decreases, and then tritium is implanted from the top as well. And so what we care about here is the temperature distribution in the divertor monoblock, knowing that there is some water cooling channel in the center here. So looking at the temperature distribution and the tritium distribution in the system. So the first version of it, the version that was published, was coupling heat conduction and TMAP8. Here we try to push it a little bit further, where we couple it also with the thermal mechanics. And we also extended it to 3D here. I think it makes the thermal mechanics quite a bit more interesting. So those are the results. We should have a GIF that plays. It doesn't seem like it's playing, unfortunately. That's a bummer. All right, I'll send some. I'll send those videos somewhere else in the chat. But hopefully, what you should see here is the temperature increasing from the top. And actually, I think I have some of the results here. So that's what you would see. So you would see the temperature from the top, and then you see tritium accumulating from the top like this. And you can also visualize the von Mises stress here. So you can see, for example, higher stress at the layer, the interface between the copper and the chromium, the copper and the tungsten. Sorry. The next step of this was to couple also the neutronics calculation to provide some heating rate for the heat conduction. So now, instead of having only the heat flux coming from the top, we also have some volumetric heating due to the neutrons heating the material. Unfortunately, it seems like those videos are not playing either. That's really a bummer. Again, I'll share that in the chat. But with the neutronics, what you see is instead of having just the temperature flux coming from the top, you see some more volumetric heating, which means that the temperature profile, for example, is quite different, because instead of having really a gradient from top to bottom, you also see some high temperatures at the bottom here, especially here far from the coolant. And so that really transforms the temperature distribution. That, of course, affects the von Mises stress and the tritium distribution, which really highlights the importance of coupling the physics. Unfortunately, here, big bummer, the videos are not playing, but I'll send that in the chat. And then in the future, what we're working towards is coupling directly the neutronics calculation to also account for material degradation, which of course potentially could change some of the thermomechanics properties, but also change the amount of traps for tritium transport in the divertor monoblock, which would further affect the tritium distribution. One thing I wanted to highlight here is INL is also supporting the VTB. So the VTB is the virtual test bed for fusion. So we are adding fusion cases. You can see here, for example, the divertor monoblock case, where we provide all the documentation, input file, and code that you need to reproduce those cases. And as we do further development, more cases will be added there. I think I'm running shortly out of time, so I wanted to highlight here. So MOOS can is a proven system for complex multiphysics simulation, and we're leveraging that to do key simulation for tritium transport and general component behavior, material behavior for fusion. The open source aspect of it, coupled with the very strict software quality assurance processes that we leverage, really enables effective collaboration, builds trust, and the licensing approach that we use also enables public-public and public-private partnership. And yeah, I'll leave it at that. And I want to acknowledge the funding sources and the collaborators. And yeah, reach out if you have any questions. Thank you.
Awesome. Thanks so much, Pierre. It's a great talk. Can everybody hear me okay? I just want to check because I got a connection notice. Great. I see head nods. That's a good sign. Excellent. So there's one question coming from Luis Garcia. How would you input an OpenMC heating CSV output into a moose simulation? Is it using the heat source module?
So that's a good question. So we have different ways of doing this. If you want to do that OpenMC simulation separately from the moose simulation, you can input the volumetric heating source. But here, what we're doing in the simulation that I was showing, actually wanted to show since the video didn't work, but is that we can directly use the multi-app system in Moose so that you have a main application that sends everything, runs the OpenMC for you automatically with the parameters that you gave it, and then directly takes the volumetric heating source and sends it to the rest of the Moose application. And you can send information like this both ways. So in that case, you don't need to handle the data transfer at all manually. It's all done within the multi-app system. Hopefully that, Louis, let me know if that wasn't clear enough.
Awesome, thanks. I have one short question, hopefully. Maybe it's actually probably a bigger question, but there are many different mesh element types that are supported in Moose, and I'm just curious about the Moose's ability to cross-map those different element types. I know that, like, for example, in Cardinal, there's an intermediate mesh between the OpenMC domain and the NECRS domain, but like high order elements to linear elements and things like that, it's able to interpolate between those domains. Is that right?
Yeah, so it can interpolate between those domains. That's one of the things that Mahmoud was looking at is, really making sure that, for example, the surface mesh that you might use directly corresponds to the volumetric mesh that you're using in Moose. So he did some conversion studies here, making sure that, as you refine the meshes, they all, still correspond well to each other and limit drastically the amount of errors that you introduce because of the differences in mesh. So that's really, streamlining this workflow. He also showed that when your surface mesh and volumetric mesh do not correspond directly, then that can cause issues, right? I'll put a link in the chat with that specific papers that goes into that specifically. It's actually not I don't think it's a small question, a small issue, because it can actually have significant either impact on your results, or it can really slow down the workflow for engineering development, especially if you want to do optimization of your geometry. And if you have to redo all the different mesh and make sure they correspond every time, then that takes a lot of time.
Yeah, absolutely. I think we saw that too when we were doing some work with Cardinal. So
yeah.
But yeah, I think some more recent workflows out of Qubit and other meshing workflows are making it a little easier to generate those conformal surface meshes to the TET mesh or whatever volumetric mesh you have. So
yeah, great. And I think in Fusion it's even more key because some of those geometries are quite complex. The curves are quite sophisticated.
Agreed.